Alright, welcome to the second day of algebra class. So let's take a bit to talk about the homework problems from yesterday. The first problem from yesterday was find all possible values of a, b, given that a plus b equals 2 and a to the fourth power plus b to the fourth power equals 16. So the hint I gave last time was to square both sides of a plus b equals 2. And if you square both sides of that, you'll get a squared plus 2ab plus b squared equals 4. And then if you rearrange a little bit, you'll get a squared plus b squared equals 4 minus 2ab. Now let's take a little bit to talk about why you have to rearrange a little bit, why you have to subtract 2ab from both sides before squaring again. And the reason is that if you square it again as it is, then you're going to get a lot of weird terms with various powers of a and b in it because of that 2ab in there. So if you're going to square this equation again, you're going to want the 2ab to be away from a squared and b squared. If it's 4 minus 2ab, if you square that, if you square that quantity, if you think about it, that's going to look a lot nicer. You're not going to get weird terms in there. And also, squaring a squared plus b squared, that gets us a to the fourth plus 2a squared b squared plus b to the fourth. And ab is what we wanted all along. And we have a to the fourth plus b to the fourth. We know that's 16. So that's why squaring that equation, the rearranged equation, a squared plus b squared equals 4 minus 2ab, that's much better to square than just squaring a plus b equals 2 twice without doing anything. So if we substitute in a to the fourth plus b to the fourth equaling 16, then the left side of the equation, a 16 appears there. And then I am going to subtract 2a squared b squared from both sides. Now when we squared a squared plus b squared on the left side, we got a to the fourth plus 2a squared b squared plus b to the fourth. But on the right side, we're going to get 16 minus 16ab plus 4a squared b squared. And as you can see, the 4 is being squared, and the 2ab is being squared, and then the middle term is that minus 2ab, or minus 2 times 4 times 2ab. Okay, and then we get 16 minus 16, we get 16 equals 16 minus 16ab plus 2a squared b squared. But from this, there's just a 16 on both sides, so we can cancel that out. Or in other words, we just subtract 16 from both sides. And then we're going to get 0 equals negative 16ab plus 2a squared b squared. And I'm just going to rearrange those terms just a little bit so that we have the 2a squared b squared minus 8ab on the right side equaling 0. And notice throughout that process, you can cancel a 2. So the 16ab is going to turn into 8ab, and the 2a squared b squared is going to turn into a squared b squared. And that's because every term in the equation has a factor of 2, so we can just cancel that out. Right? So then at this point, I moved everything to one side so that we get 0 equals a squared b squared minus 8ab. Now here's an important point. On the step before, I had 16ab equals 2a squared b squared. And of course you can cancel a 2, but it looks like you can also cancel an ab from both sides. And if you did that, you would get 8 equals ab, right? And of course that is one of the solutions. But when we cancel ab from both sides, we can only cancel ab from both sides if we know that what we're canceling is not equal to 0, right? So we can always cancel something from both sides of an equation if we know it's not equal to 0. But we don't quite know that, right? When the question says find all possible values of a, b, it could be 0. So we have to keep that in mind. And so one way to not make that error is to just get everything to one side and factor out the AB. And if we factor out the AB, we get 0 equals AB times AB minus 8. So at this point, we have 0 equals AB times AB minus 8. Now, there is a fact about, there's a fact called the zero product property, and this just says that if two things multiply together to give 0, then one of the things must have been 0, right? Because if we have, say, for example, let's say that x times y equals 0, then we know that either x is 0 or y is 0, or they're both 0, right? It's not possible that they're both non-zero. So to figure out what AB is, really, I mean, we have 0 equal to AB times AB minus 8. Either AB is equal to 0 or AB minus 8 is equal to 0, or in other words, AB is equal to 8. So those are the two possibilities, and those are the two possible values of AB. So that's where the possible values comes in, and it's not just one possible answer, and that's because it was a quadratic equation in terms of AB, and canceling out AB takes away that option of AB being equal to 0. So we don't want to cancel that out, because we can only cancel things that are not 0, and it turns out that AB equals 0 is one of the possibilities. So instead of canceling it out, just bring everything to one side and factor it out. And of course, remember, factoring out just means doing the reverse of the distributive property. If you know how to distribute across like something times, in parentheses, something plus something else, of course you use the distributive property. And if you go backwards, that's called factoring out. Okay, so let's move on to homework problem number 2 from yesterday. Okay, so homework problem number 2. In this problem, the question is also find all possible values of a plus b. So we saw in the last problem that there were 2 answers, right? There were 2 possibilities. In this case, there's also going to be 2 possibilities. So there's also going to be a way to like accidentally forget about one of the options and just get one of them as an answer, just like the last problem. So when we get to that point, we'll talk about we need to make sure that we get both of them. Okay, so we have a cubed minus b cubed equals 24, and we have that a minus b is equal to 2, and we want to find out what the possible values of a plus b is. The first thing that might jump out at you is that a cubed minus b cubed is a difference of cubes. And yes, I think it is possible to solve it that way, but it's a little bit harder to solve it that way if you factor that and then work with that factorization. So instead, we're going to do the way that I suggested, which is cubing both sides of a minus b equaling 2. Now, we didn't talk about what the general form is for cubing a binomial, and remember, a binomial is just something plus something else. If we're cubing a binomial, a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. And that's kind of hard to remember, but you can also just multiply it out and see what you get. Okay, so if we do multiply out a minus b cubed, we're going to get a cubed minus 3a squared b plus 3ab squared minus b cubed. And of course, 2 cubed is 8, so we're going to get 8 on the right-hand side. And this is useful because when we cubed a minus b, we get a cubed minus b cubed showing up in the expression. So the a cubed minus b cubed, even though that the a cubed is not right next to the minus b cubed in that equation, of course, because addition is commutative, we can always move that term right next to the a cubed. So we can replace a cubed minus b cubed with 24. We're going to substitute that into the equation. And then we're going to factor out something from the middle 2 terms there. So as you can see, the middle two terms there, the minus 3a squared b and the plus 3ab squared, that is, those are a little bit kind of messy terms a little bit, but there is something that they have in common. They have a lot in common, actually. The first one has a factor of 3, it has a factor of a and a factor of b, and the second one also has a factor of 3, a factor of a, and a factor of b. The first term has an extra a, and the second one has an extra b. So if we factor out a 3ab, then what's left is going to be something super useful. And that shorthand, LHS, just means left-hand side. It's commonly used in math to just have a shortcut. RHS is often called the right-hand side. And that becomes useful when we're referring to the left or right sides of an equation. Okay, so this gives us 24 minus 3ab times a minus b equals 8. So obviously the right-hand side of the equation stayed the same, and we substituted in 24 for a cubed minus b cubed. Now factoring out the 3ab. So the first term, minus 3a squared b, plus 3ab squared. The first term there is negative and the second one's positive. So if we factor out a minus 3ab, then we're going to ask ourselves, well, what's left? What's left in that term when we factor out a minus 3ab? And for the first term, what's left is an a. And in the second term, if you factor out a minus 3ab, because the term was positive to begin with, if you factor out a minus 3ab, then we're going to be left with a negative b. And that's because, well, a negative b times a minus 3ab will give us what we had originally, which was the positive 3ab squared. Okay, so if we factor out a minus 3ab, we're going to write down what's left when we factor out that. In the first term, it's an a. In the second term, it's a minus b. So that's where the a minus b comes from. Okay, so we're at the point where we have 24 minus 3ab times a minus b equals 8. And we know what a minus b is because they tell us, so that's awesome. And that's nice, right? This problem's kind of cool because the a minus b just kind of popped out. It just popped out after we factored out the minus 3ab. So let's substitute a 2 in for that. And now we have 16 equals 3ab times 2. Right? I just subtracted 8 from both sides and then moved that 3ab times a minus b term to the other side. I'll often do arrangements like that just because I always like to have my equations look just like, you always have freedom to rearrange equations, so I just want to make it look the best. So hopefully you see how we get to 16 equals 3ab times 2, and of course 3 times 2 is 6, so we have 16 equals 6 times ab, and then if you divide by 6 on both sides, 16 over 6, that's the same as 8 over 3, so ab is equal to 8 over 3. So, okay, we found the value of ab now, but we really wanted to find a plus b, right? We were given a minus b, we were given a cubed minus b cubed, and we did all this work, but we only found ab. However, finding ab is useful. And here's an important point that I want you to think about. We're looking for a plus b, and we have ab, right? And now ab and a plus b, those terms, they show up in the expansion of a plus b squared, right? So if we square a plus b, we get an equation that says that a plus b quantity squared equals a squared plus 2ab plus b squared. Now we know what ab is, so we would need to find a squared plus b squared, and then we would know what a plus b is. So it'd be nice to know what a squared plus b squared is, but luckily there is a way, right? Honestly, for these algebraic problems, where they give you a certain quantity, they give you another quantity, and you have to find some other value, like problems like this one, really, you just have to try a few things. I mean, that's how I solved this. I just tried a few things, and maybe there's a little bit faster way, and that's great if you found a faster way, and it's fine if you found a longer way, as long as you get to the answer. So yeah, just try things, and the next thing that turns out to be super useful is squaring the identity a minus b equals 2. Now earlier we cubed this, right? We cubed a minus b equals 2. We cubed both sides. Now we're going to square both sides. And it turns out that that's going to be useful. So if we square both sides, on the left we get a squared minus 2ab plus b squared, and on the right we get 4. Okay? And of course, we know what AB is equal to. AB, we just found out, was equal to 8/3. So we have a minus 2AB, so minus 2 times 8/3, that's minus 16/3. So if we add 16/3 to both sides, then we'll get a squared plus b squared by itself. And 4 was on the right side, and then when we added 16/3, we got to add 16/3 to 4. Common denominator, okay, looks like 3. So 12/3 plus 16/3 is 28/3. So that's the value of a squared plus b squared. Okay, so we have a squared plus b squared, 28/3. So now we can go back to that equation of a plus b quantity squared, which was a squared plus b squared plus 2ab. We know what a squared plus b squared, it's 28/3, and we know what 2ab is, it's 16/3. So if we add those two together, we get 44/3. So now we're at the point where a plus b quantity squared is 44/3. Now, that's exactly, well, we needed to find a plus b, and we have a plus b squared. So if what we want, if the square of that number is 44/3, there's two possibilities for what a plus b can be. It's either the square root of 44/3, right? Because the square root of 44/3 times the square root of 44/3 is just 44/3. But we also have the negative of the square root of 44/3, because a negative times a negative is a positive. So that gives us also 44/3, right? So there's always two square roots of a number. Yeah, and of course there's one slight little subtlety about having two answers for the square root. So if you see something like, what is the square root of 9, and you see like the little radical symbol, right? Like that little thing that is like, it's a radical symbol. If you have the square root of 9 that looks like that, that always assumes you take the positive square root. So the answer to that would be 3. But if you see something that says solve the equation x squared equals 9, well, there's two values of x that work, right? 3 and -3. So if you see that something squared equals a number, then there's two possibilities for what's inside, what's under the square sign. But if you see the square root symbol, it's just kind of a convention in mathematics that means we just take the positive square root. So that's why you often see like plus or minus, that symbol in front of a square root sign, because the square root sign assumes the positive square root. Okay, so let's move on to homework problem 3 from yesterday. Now this one was kind of heavy on the numerical side. However, this still we needed to use an algebraic trick to solve this one. So let's talk about this one. We need to find all prime factors of 3 to the 18th power minus 2 to the 18th power. Okay, so right away we see that this is a difference of 18th powers. And of course, the number 18 is divisible by 2, and it's also divisible by 3. So that means that both 3 to the 18th power and 2 to the 18th power, they're perfect squares, and they're also perfect cubes. So that means we have a choice. Are we first going to factor this as the difference of squares? Or are we first going to factor this as the difference of cubes? Now, there's a little known fact within the problem-solving community, and the fact is that if something factors as a difference of squares and a difference of cubes, it's always better to factor it as a difference of squares first. Even though factoring it as a difference of cubes might be like, oh, well, this is a higher power that we're factoring it as, and where, it's kind of harder to factor it as a difference of cubes. Like it's harder to remember the formula than it is to factor it as a difference of squares, so we might as well do the harder one because we know that both of them apply. But really, if you're given a choice, like this, where the problem factors as a difference of squares and a difference of cubes, factoring as a difference of squares is always better. So always try that first and see if it works, and then if it doesn't work, go to difference of cubes. And that's just a little tip for you. And I know it would have been useful to know this yesterday, but I thought it was instructive to maybe have you just try these yourself and see what you try, and then tell you the tip today. So yeah, so let's start by factoring this as the difference of squares. So 3 to the 18th power, that number is equal to some number squared, and that number is 3 to the 9th power. So 3 to the 9th power squared is 3 to the 18th. 2 to the 9th power squared is 2 to the 18th. So we can factor this as 3 to the 9th minus 2 to the 9th times 3 to the 9th plus 2 to the 9th. And then we can notice that, well, both of these factors, both of them, well, the first one's a difference of cubes, and the second one is a sum of cubes, right? They're not, the first one's not a difference of squares, but it is a difference of cubes. So we can factor both of them, and it's really important to see, like, okay, well, what's A and what's B? You know, if I'm gonna think of this 3 to the 9th minus 2 to the 9th, if I'm going to think of that as a cubed minus b cubed, you better correctly identify what a is and what b is. And it turns out that a is going to be 3 cubed, because 3 cubed cubed is 3 to the 3rd power, and then in parentheses to the 3rd power, and you multiply the exponents, you get 3 to the 9th. So 3 cubed, that's the correct value of a. The correct value of b is 2 cubed, right? Because 2 cubed, and then in parentheses, all cubed, you have to multiply the exponents, and you get 2 to the 9th. So, great. So a is 3 cubed, and b is 2 cubed. So the factorization is a minus b times a squared plus ab plus b squared, and if you do all that, you get 3 to the 6th plus 3 cubed times 2 cubed plus 2 to the 6th. And I left it as 3 cubed times 2 cubed for a reason, instead of 6 cubed. Okay, so then we need to factor the sum of cubes. Okay, so you need to recognize 3 to the 9th plus 2 to the 9th as something cubed plus something else cubed. Well, if this is of the form a cubed plus b cubed, it's the same a and b as in the difference of cubes over there. So we're going to get 3 cubed plus 2 cubed times the quantity 3 to the 6th minus 3 cubed times 2 cubed plus 2 to the 6th. Okay, so that's pretty factored, right? That we factored that. We have, looks like 1, 2, 3, 4, 5, 6 factors there. Wait, no, sorry. Actually, there's only 4. I miscounted. Yep, there's 4 factors, which is pretty good, right? 3 to the 18th power is a huge number, and 2 to the 18th power is also huge. It's just not reasonable to try to compute those by hand, or even with a calculator, subtract and then try to factor it. That's just insane. So it's great that we have a factoring trick. So finally, we're just going to compute by hand what these parentheses values are. So 3 cubed is 27, minus 8 is 19, 3 to the 6th power is 729, 3 cubed is 27, 2 cubed is 8, 27 times 8 is 216, 2 to the 6th power is 64, and then we have 27 plus 8 is 35, that's the third factor, and finally we have 3 to the 6th, which is 729, minus 27 times 8, which is 216, plus 64. So, and then if we simplify the 729 plus 216 plus 64, we get 577. Actually, no, we get 1009. Sorry, I just switched the order there. And then if we simplify 729 minus 216 plus 64, we get 577. And you should all know that 5 is prime, 7 is prime, and 19 is prime. It's a little bit harder to check that 577 and 1009 are prime. I suppose you could just assume they are and hope for the best, hope you're right. But if we were to check, the square root of 577. Now, let's see. I know 625 square root is 25. 576 is 24. Okay, there we go. So, the square root of 577 is roughly 24 point something. So the highest prime you need to check is 23. So we need to check 2, doesn't work. 3, doesn't work. 5, doesn't work. 7, you think for a little bit, oh, doesn't work. You try 11, doesn't work. Try 13, doesn't work. You try 17, and then you try 19, then you try 23, and then you try nothing. Yeah, that's it. 23 is the last prime you need to check. And if all of those primes fail to divide the number, then we know for certain that the number is prime. Okay, and then we do the same thing for 1009. 1024 is a square number that's pretty close. That's 32 squared. And I just know that because 1024 is 2 to the 10th, and 2 to the 5th is 32. So the highest prime we need to check there is 31. So we need to check 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and 31. And as soon as one of those primes goes into it, then we know that we can factor it. But if all of those primes fail to go in, then we know for sure that 1009 is prime. Okay, so this was yesterday's challenge homework problem. The problem was find two 4-digit numbers whose product is 4 to the 8th power plus 6 to the 8th power plus 9 to the 8th power. So we need a 4-digit number times a 4-digit number equaling that expression. And each of the terms in that expression is really, really large. So you definitely aren't going to compute each of those, add them together, and try to number crunch. That's just not reasonable at all. However, let's try to factor this. So step 1, let's write everything in terms of powers of 2 and powers of 3. Because if you notice, the base of the exponents on those three terms, we have a 4, a 6, and a 9. Well, that's 2 squared, 2 times 3, and 3 squared. So that means it might be nice to try doing something with that. So if we write everything in terms of 2s and 3s, then we have 2 to the 16th power plus 2 to the 8th power times 3 to the 8th power plus 3 to the 16th power. So this almost looks like an expanded version of x plus y squared, right? This almost looks like x squared plus y squared plus 2xy, except the middle term, it doesn't have 2 times the number, it just has the two numbers multiplied. So in particular, this looks like an expanded version of x plus y squared, where x looks like 2 to the 8th power, and y looks like 3 to the 8th power, okay? So if we let x be 2 to the 8th power and y be 3 to the 8th power, then, well, this expression we have is almost 2 to the 8th plus 3 to the 8th squared. In fact, so we can just set this whole expression, we can just say what it's equal to. Well, it's equal to 2 to the 8th plus 3 to the 8th squared, but if we compute 2 to the 8th plus 3 to the 8th squared, we're going to get 2 to the 16th and 3 to the 16th, but we're also going to get that middle term, the 2ab term, and that's going to be 2 times 2 to the 8th times 3 to the 8th. But we only have 2 to the 8th times 3 to the 8th. So since the term we get from squaring 2 to the 8th plus 3 to the 8th is 2 times 2 to the 8th times 3 to the 8th, we're going to subtract a copy of 2 to the 8th times 3 to the 8th to get just 2 to the 8th times 3 to the 8th. I hope that makes sense. But try to expand 2 to the 8th plus 3 to the 8th squared if you're confused a little bit, and you'll see that if we expand that and then subtract 2 to the 8th times 3 to the 8th, we'll get the left side of this equation. Okay. And now at this point, when we wrote our number as 2 to the 8th plus 3 to the 8th squared minus 2 to the 8th times 3 to the 8th, we can notice that actually, like, this is a difference of squares. This is a difference of squares. The first one's a square, obviously, But the other side, the right side of the minus sign there, that's actually a perfect square as well. So that's equal to something squared. Now, what thing squared is it equal to? Well, it's equal to 2 to the 4th times 3 to the 4th squared. So we're going to write this as a difference of squares, where, okay, so a difference of squares, that means a squared minus b squared equals a minus b times a plus b. Well, what's a and what's b in this situation? A is just 2 to the 8th plus 3 to the 8th, and b is 2 to the 4th times 3 to the 4th. So if we do that, we get 2 to the 8th plus 3 to the 8th minus 2 to the 4th times 3 to the 4th. All of that times 2 to the 8th plus 3 to the 8th plus 2 to the 4th times 3 to the 4th. And then at this point, we're just going to compute these numbers because they're small enough that we can probably compute this out in not too long of time. So 2 to the 8th power is 256. 3 to the 8th power, I didn't have that one memorized, so I had to compute that. 6561. And then 2 to the 4th times 3 to the 4th, that is 1296. That's 16 times 81. Not too long to multiply together. And then we just had the same thing, but plus 1296 instead. And if we do that, like, if we figure out what those two numbers are, the first one's 5,521, and the second number is 8,113. So pretty cool, in my opinion. We started with a really like complicated number, a really big number that's really simple to write, but we're asked to find two numbers that both have 4 digits that multiply together to give this number. Now notice we didn't have to do any 4-digit multiplication at all in here. The worst thing was 2-digit times 2-digit maybe, or 3-digit times 1-digit if you're computing 3 to the 8th. But really, none of the computations were that bad. So you can see how, like, factoring numbers or just recognizing that it has a certain algebraic form, it's super useful. So you should always be on the lookout for algebraic identities just kind of surreptitiously hidden within a problem. Okay, so take a minute to look over the homework problems from yesterday. Make sure that you have all the answers. Make sure you understand as best you can how these problems are solved. Of course, if you're lost or if you have some lingering questions about this stuff, make sure to ask me tomorrow or tonight in an email. It's totally fine to reach out to me in that way. These problems are hard. I gave you problems that use algebra material. Like the material itself isn't too bad if you practice it. But the problems I've been giving you are difficult applications of that algebra material. And I think that difficult application of the algebra material is super helpful in understanding the material itself, and it makes it kind of fun. Okay, so let's just recap the things that we've been talking about yesterday and with the homework problems that were given out yesterday and that we covered today. Let's just recap the different algebraic formulas that we have used. Okay, so the first one we talked about was in the lower right hand corner over there, when we have a squared minus b squared. That and there's 3 little lines there, and that just means congruent. I'm not sure why they didn't use an equal sign, but if you use 3 lines, it just means congruent, which means like they're technically different like things, but they're exactly the same. They have the same information. So yeah, so a squared minus b squared, that always factors as a plus b times a minus b, right? Or a minus b times a plus b, right? It doesn't matter what order you write down a plus b times a minus b, because multiplication of numbers is commutative, right? It has the commutative property, so it doesn't matter what order. And then, of course, if we have something that's like a plus b times a minus b, right? Now remember, it doesn't matter what a and b are. They could be complicated algebra expressions. They could be any number They could be any combination of variables, as long as it's something plus something else times that first thing minus that second thing, right? So we can always go back and forth there. And same thing for the rest of these identities. Like if we go up a little bit, a plus b quantity squared is up there. If you've heard of FOIL, some teachers today don't like it because it kind of takes away from the term that's more accurate, which is the distributive property, which is what we're using. But FOIL is a nice little acronym just to help you remember how to multiply binomials together. Now, when you're multiplying like something plus something else times something else plus something else, it doesn't have to be the same thing you're multiplying. You can multiply two different binomials, but here it's just the same, a plus b times a plus b. And the f in FOIL is just first, and then the o is outside, the I is inside, and then the L is the last. So the first is just multiplying the first ones together, the last is multiplying the last ones together, but don't forget the o and the I, the outer terms together, and the middle terms together. And if we do that and add them all together, we get a squared plus 2ab plus b squared. Okay, and then on the left are some harder cubic kind of identities. They're a little bit harder, but they're extremely useful in problem solving. We have the sum and the difference of cubes up there on top, and then we have the cube of the sum of two things and the cube of the difference of two things. Now, pay close attention to the difference between the things in the top box up there and the things in blue and orange down there, right? They're totally different, right? A cubed minus b cubed is not the same thing as a minus b in parentheses raised to the third power. And a cubed plus b cubed is not the same thing as a plus b in parentheses raised to the third power. They're totally different things, right? If you take a plus b in parentheses raised to the third power, you're going to get a cubed and b cubed as two of your terms, but you're going to get two more terms, right? Because if you do a plus b times a plus b times a plus b, that's 8 things that you have to multiply together, and some of those are going to collect into like terms. So they're not the same. However, a cubed plus b cubed, if you have just a cubed and just b cubed, you can factor it, right? You can factor it as a plus b times a squared minus ab plus b squared. And if you have just a cubed minus b cubed, you can factor that as a minus b times a squared plus ab plus b squared. So definitely study these and memorize them if you don't have them memorized yet. They're super important. Make sure that you're able to multiply out the things. Like for the sum and difference of cubes, make sure you're able to multiply out the right side, and then terms cancel out, and make sure you're able to get the left side of the equal sign for both of them. And then for the bottom one, make sure you can multiply out the left side and get the right side, right? Now for the bottom two, I always remember a cubed plus 3a squared b plus 3ab squared plus b cubed, and they chose to factor the two middle terms a little bit, just to show you that 3 and one copy of a and one copy of b, they both appear in both terms, so we can factor them out, and there's an a left in the first term and there's a b left in the second term. It's just to show you that you can do that if it's helpful for the problem, but both forms are fine. And likewise for a minus b in parentheses to the third power, we have a minus 3a squared b and a plus 3ab squared. So notice that we can factor out a 3ab, or we can factor out a minus 3ab, right? If we factor out a 3ab, there'd be left a minus a and a positive b, and a minus a in the first term and a positive b in the second term. But if we factor out a minus 3ab, then we get a positive a in the first term and a minus b in the second term. So yeah, make sure you remember all of these formulas. Make sure you are able to recognize these formulas when they appear in different expressions. Remember, we have a's and b's. on this page, but A can be a complicated thing, and B could also be some complicated thing. Probably not too complicated, or else it'd be too hard to recognize it. But A could be something like 2x, and B could be something like 3y squared, maybe. So always be on the lookout for things like that. Okay, let's move on to the next slide. Okay, so I do have a warm-up, 3 warm-up problems for you. The first one, I want you to simplify completely, right? So we have a fraction times another fraction times another fraction. Now, when we multiply fractions together, the numerators just multiply, and then the denominators multiply together. So make sure you remember that the product of these 3 fractions is really just one big fraction, where those 3 things are multiplied on the top, and those 3 things are multiplied on the bottom. And obviously, you're gonna need to factor some of these terms, and a lot of things will cancel out. Okay, and then the second one, I want you to factor that completely. And the hint is that you're gonna want to do something with the 3 terms that have m and n in them. You're gonna do something with that first, and then you'll factor everything along with the x squared in it. And then the third problem, just factor that as completely as possible, and say how many factors there are at the very end of the factoring, when you can't factor it anymore. Okay, so good luck. I'll give you some time to work on these, and yeah, then we'll go over them. Okay, hopefully you had enough time to work on these. Let's talk about the first one. So we're going to factor fully anything that can be factored, okay? So for these three fractions, the a cubed minus b cubed, the a cubed minus 1, that can be factored because we have a cubed and the b is just equal to 1. So it is like 1 is a cube, like, right? So like 1 cubed is itself. So that factors as a minus 1 times a squared plus a plus 1. And then you might notice that a squared plus 2a plus 1, that's actually a plus 1 quantity squared. And then the third one on top, a squared minus a plus 1, it's really not clear if that factors or not. It doesn't, so that's just going to stay the same. And then in the bottom, we have a squared minus 1. And obviously that's a difference of squares where b is equal to 1 again. So a minus 1 times a plus 1. And then we have a cubed plus 1 in the bottom. So that is a sum of cubes. So we have a cubed plus 1 cubed. Okay, so we're going to have a plus 1 times a squared minus a plus 1. That's how that's going to factor. And then, of course, we have an extra factor of a plus 1 on the bottom from that third fraction. And then we're going to cancel everything that we possibly can. So right away, we see that there's an a minus 1 on top and bottom, so we'll cancel it. We have a plus 1 squared on top, and we have 2 of them on bottom, so all of those cancel. And then we have a squared minus a plus 1 on top, and a squared minus a plus 1 on the bottom. So all of those are going to cancel out, and that's just going to leave us with a squared plus a plus 1 on the top, and then we'll have a plus 1 on the bottom. Okay, so it's just gonna end up being a simple fraction where the numerator is a squared plus a plus 1, and the bottom is a plus 1. And this cannot be factored any further, so this is the final answer. Now, I do also want to mention, when are we allowed to cancel things? So, in this situation, there's just a product of things on top and a product of things in the bottom. So, we can cancel something if it's a factor of both the top and the bottom. So, if something is a factor of the top, that means that that thing is being multiplied by the rest of the numerator, right? And we can see that everything in the top, everything, like if you pick any one of those things in parentheses, it is being multiplied by the rest of the top. And the denominator here, if you pick any of the things in parentheses down there, it's being multiplied by the rest of what's on the bottom. Okay, now that is in stark contrast to the simplified fraction here. The simplified fraction here, you may think that, oh, there's an a on top and there's an a on the bottom, we can just cancel it. That is one of the most common mistakes in algebra. We can't cancel something unless it's being multiplied by the whole top or being multiplied by the whole bottom. So if we were able to factor out an a from the top and bottom, then we could cancel an a. But it's precisely because of the plus 1 on the top and the plus 1 on the bottom that will never happen. So nothing is able to be canceled at all from the top and bottom, because nothing is being multiplied by everything. So if a was in each term, right, if we had something like a squared plus a cubed over a plus a squared, then we could factor out an a, because there was an a in each term, and when there's an a in each term, you can factor out the a, and then suddenly the a is being multiplied by the rest because it was factored out. So we can't cancel an a in that simplified fraction, and we cannot cancel a 1. We can't cancel the 1 either in that simplified fraction. So be very, very sure that you remember that, because it's one of the most common mistakes, and it leads to a lot of missed questions in class and competitions as well. And also, if we're going to write if we're going to simplify a fraction, just like if the fraction had numbers on the top and the bottom, and we're going to take out the greatest common factor of the top and bottom, the same thing with fractions with algebraic expressions on top and bottom, right? we want to make sure that we cancel out anything that appears in the top and bottom as a factor. Okay, so let's factor this completely. We have x squared plus 2mn minus m squared minus n squared. Okay, so you might kind of in your mind know that, well, if there was a plus m squared plus 2mn plus n squared, well, that's m plus n in parentheses raised to the second power, right? That's the expanded form of that. However, there's a couple negative terms here. So you might think, well, maybe it's m minus n in parentheses raised to the second power. So because the only thing that's off about these terms are, like, whether it being plus or minus, if each term is the negative of what we want it to be, then we can factor out a -1 from each of those terms, which will be super handy. And that's exactly what we do. So as you can see, the second line here is x squared minus that whole quantity. So really what we have is we have a minus m squared up there. So we're going to minus a positive m squared. And because the 2mn was positive here, we're going to subtract off a negative 2mn, right? That's the same thing as adding 2mn. And we're going to subtract an n squared. So make sure you check with yourself to see if you distribute that negative sign in that second line there to each of those three terms, that you end up with the top line there, right? Make sure we factored out the negative correctly. And then you might recognize what's in parentheses there. M squared minus 2mn plus n squared, that is the expanded form of m minus n in parentheses squared. So we have x squared minus that, right? And now, oh, it looks like I forgot to typeset the final step, but I'll just say it. So this is a difference of squares, right? We have x being squared, and then we're subtracting off m minus n being squared. Okay, so if we have an a squared minus b squared situation, that's going to factor as a minus b times a plus b. So then a is equal to x, of course, and b is equal to m minus n. Now this is going to be x minus m plus n, all in parentheses, times x, sorry, I'm going to start over. Okay, so obviously when we have a squared minus b squared, we need to have a minus b, and we need to have a plus b. So we need both factors here. So let's do the negative first. Let's do a minus b. That's going to be x minus m plus n, all in parentheses. Those three letters there in parentheses. All of that times, we're going to begin our left parenthesis. We're going to do x plus m minus n. And then insert the right parenthesis there. So that's going to factor. It's going to factor like that. And then that is the complete factorization of x squared plus 2mn minus m squared minus n squared. So notice how we had to first recognize that the terms involving m and n looked suspiciously like the expanded form of m minus n squared, except perhaps off by a factor of -1. And of course, since, if that was a sum of squares, we wouldn't be able to factor it, right? If it was x squared plus something else squared, that's not factorable. So we'd better hope that it was x squared minus something else squared, which is exactly what it ended up being. We just need to get the minus signs right. And also notice how each term besides x squared was the negative of what it needed to be to look like m minus n squared. And that's why we factored out a -1. So hopefully you can see how factoring out the -1 helped us realize that it was some x squared minus something else squared. And then finally the last step, I'm sorry I forgot to put it there, but it's x minus m plus n times x plus m minus n. Sorry. All right. So now we have our third warm-up problem. We need to factor x to the 9th power minus x as completely as possible, and then we need to say how many factors there are at the very end. Okay, so step 1, there's definitely an x in both of the terms. So because it's x to the 9th minus x, we can factor out an x, and then we'll get x times the quantity x to the 8th power minus 1. Okay, so now we need to deal with that x to the 8th power minus 1. Now, that is a difference of cubes, and it's also a difference of squares. Now, I did say before that it's probably better to do the difference of squares if it's both a difference of squares and a difference of cubes. If you do factor this as a difference of squares, that's fine, but it is harder to see the next trick that comes in the problem. So just for the sake of clarity, I'm going to factor this as a difference of cubes. And again, either one is fine. Like, because x to the 8th minus 1, because both apply to it, it's a difference of squares and it's a difference of cubes. So we can pick either path, right, to factor. And you know, I said as a general principle, try to factor as a difference of squares before factoring as a difference of cubes. But in this one, I just think it's more instructive to do as a difference of cubes because there's a middle term that'll come out in what's in the second part of it. So if we factor as a difference of cubes, we get x squared minus 1, right? So the a is going to be x squared and the b is just 1. And then what's left over is x to the 4th plus x squared plus 1. Now, x squared minus 1, that is a difference of squares, right? It's x squared minus 1 squared. So that's x minus 1 times x plus 1. Then we got that taken care of. And now it might look like that we might not be able to factor the other thing. Because it doesn't look like it's a sum or difference of cubes or anything like that. However, the point of the problem at this point is, well, we did see before how something can look like the expanded form of x plus y quantity squared, right? X plus y quantity squared is x squared plus 2xy plus y squared. And we saw, like, I think at least twice before, where the middle term, instead of being 2xy, it was just xy. Now, it looks like that's going to happen here, for sure. X to the 4th plus x squared plus 1, that looks almost suspiciously like the quantity x squared plus 1 raised to the 2nd power, right? And the bottom of this, the bottom text here in bold, actually describes this. So the hardest part of this problem is probably factoring that expression with x to the 4th. You would have had to notice that it looks suspiciously like the quantity x squared plus 1 all squared, except it was off by x squared, right? So what do we get when we square that x squared plus 1? We get x to the 4th plus 2x squared plus 1. But what we have in the problem is x to the 4th plus 1x squared plus 1. So what we really have is we have x squared plus 1 quantity squared, but if we subtract x squared from that, then we get what we actually have. So make sure you understand how squaring x squared plus 1 and then subtracting off an x squared gives us x to the 4th plus x squared plus 1. And the reason we wanted to factor it like that is because now it's a difference of squares, just like the previous couple problems where we had this same, where it almost looked like the expanded form. So we're going to do the difference of squares. This is a squared minus b squared. A is equal to x squared plus 1, and b is equal to x. So we have x squared minus x plus 1, and then x squared plus x plus 1. And I just chose to put the minus x and the x in the middle, just because that's how quadratic expressions are normally written. And that is the final factored expression. So that's fully factored now. So there are exactly 5 factors total in this problem. Okay, so I have one more example for you before we move on to the next concept. So here we're gonna factor x to the 8th minus y to the 8th as much as possible, but we're gonna factor it making sure that we have real coefficients instead of requiring them to be integers. And this just means that the trick that we used on the last problem, where the middle term was off by a little bit in the expanded form of the square of a binomial, we're going to use that same trick here, except we're going to allow ourselves to, even if it doesn't look like the right thing is a square, since we're factoring over the reals, it'll still work out. So, as a general heuristic, try to factor as a difference of squares before factoring as a difference of cubes. So we get x to the 4th minus y to the 4th times x to the 4th plus y to the 4th. Now, x to the 4th minus y to the 4th, that's definitely a difference of squares, right? That's x squared minus y squared. So we get x squared minus y squared times x squared plus y squared. Now, x squared plus y squared, that is irreducible, but x squared minus y squared, that factors as x minus y times x plus y. But now, you see that x to the 4th plus y to the 4th? We can actually try to factor that. So remember in the last problem where we were off by a little bit? So what does the middle term need to be if that was factorable as x squared plus y squared, all of that squared? Well, x squared plus y squared, all of that squared, that's x to the 4th plus 2x squared y squared plus y to the 4th. So this x to the 4th plus y to the 4th is missing the middle term of 2x squared y squared. We would need that middle term in order to factor this as x squared plus y squared, all of that squared. So what we're going to do is we're going to say, well, x to the 4th plus y to the 4th, that is x squared plus y squared quantity squared, but we're going to subtract off 2x squared y squared, and then that's what's equal to what we have. And then notice, this is of the form a squared minus b squared if we allow the square root of 2 to come into play. So this is a squared minus b squared. It has that form because a is equal to x squared plus y squared, and b is equal to the square root of 2 times x times y. So if we factor this as a minus b times a plus b, remember a was x squared plus y squared, and b was square root of 2 times x plus y. So we factor it as x squared plus y squared minus square root of 2 xy times x squared plus y squared plus square root of 2 xy. Now notice that if we tried to do this same trick with x squared plus y squared, it would fail. And I'll show you why. So, like, what if we tried to do the same thing with this? So if we looked at that x squared plus y squared term, we could say that, oh, well, this almost looks like x plus y in parentheses raised to the second power, except it's missing the 2xy in the middle. Well, yes, but if we try to factor it, as you can see on the screen here, we have x squared plus y squared equals quantity x plus y squared minus 2xy. That's all fine and good, except, okay, the left side of the minus sign, that's a perfect square, but the right side of the minus sign, that's not really a perfect square. I mean, if we wanted to force it to be a perfect square, I guess, then it would be the square root of 2xy. And you could factor it that way, except that's not, like, when we factor polynomials, we want each factor themselves to be polynomials. And in this case, having the square root of a variable is it's the same thing as having a fractional exponent. And we'll see that in the next couple of slides. We'll talk about fractional exponents and how to work with them. But yeah, so a polynomial is a sum of terms that have positive powers of the variable, positive integer powers. So like x cubed plus 2x plus 1 is a perfectly good polynomial. But x to the 1.5 power plus 3, that's not a polynomial because the integers, because the exponent of the variable has to be an integer. So when we factor a polynomial, the factors themselves have to be polynomials in order for it to like factor in the way that most people mean when they say factor. I mean, we could always break up x into square roots and fourth roots and cube roots and stuff like that, but that's just not what we mean. Okay, we always want full whole number copies of x lying around, and same for y and any other variable used. So just keep that in mind. We're able to factor x to the fourth plus y to the fourth as long as we're able to introduce the square root of 2. Okay? So if it says factor as completely as possible with real coefficients, then we can do that. But if it's required of us that we have to factor where all of the coefficients, and remember, coefficients is just the number being multiplied by the variables. If oftentimes it's required that the coefficients be integers. So in that case, then we can't factor x to the fourth plus y to the fourth. And we say that x to the fourth plus y to the fourth is irreducible over the integers, meaning that if we only allow integer coefficients, then it's not factorable, right? It's irreducible. It's not, you can't break it up anymore. But we say that x to the fourth plus y to the fourth is reducible, or not irreducible, or factorable over the real numbers. So x to the fourth plus y to the fourth is factorable over the real numbers, as we exhibited in this string of expressions right here above. But it's not factorable over the integers, as we can see. Well, I'm sorry. Yeah, x to the fourth plus y to the fourth is not factorable over the integers because we see that we would need a square root of 2, which is not an integer, in order to factor it. And x squared plus y squared, that's irreducible over the reals. It's irreducible over the integers. We're not able to factor that at all over anything, except for some of this kind of like pseudo factorization where we're introducing some really messy and undesirable expressions like the square root of 2xy, things like that. So, okay, just keep that in mind. Alright, so if everything looks good to you, make sure that you understand every step of this process. The hardest part for you might just be identifying what A and what B is, right? Like, if you have memorized a cubed plus b cubed equals a plus b times a squared minus ab plus b squared, the hardest part for you might just be figuring out what A is and what B is in these problems, and that's okay. It can be hard to figure out what that is. But okay, so next we're going to talk about exponents just for a little bit. This might be review for you if you're familiar with how exponents work, how we combine expressions with the same base but have different exponents. We'll review all of the rules for exponents, so get ready to write these down if you still need to remember these, because you've definitely seen at least some of them before. And then after that, we will talk about fractional exponents, which are really important in talking about square roots. So as you can see, if we have the square root of x, just know that the square root is the same thing as taking something to the 1/2 power. So x to the 1/2 power is the exact same thing as the square root of x. And we'll see that in a couple slides. But for now, let's take a look at these rules. So these are the exponent rules. Looks like there's 8 of them here. Now, the first rule is the product rule. The names aren't super important. I guess they're just useful names. You don't have to remember the names. I couldn't tell you what the names are probably, but if we have any number raised to the x power times that same number raised to the y power, then we add the exponents there. So let's say we have 3 to the 10th power times 3 to the 5th power. That's going to be 3 to the 15th power. Okay? And then if we have 3 to the 10th power divided by 3 to the 5th power, that's going to be 3 to the 5th power. Because if we have 3 to the 10th over 3 to the 5th, we subtract the exponents if it's the same base. So that's when we divide expressions with exponents. Now remember, the base, which when I say base, I just mean the number that you're raising exponents to. The base has to be the same when you're multiplying and dividing. So if you have something like 2 cubed times 3 to the 5th power, you can't do anything to simplify that, because the base of one number is 2 and the base of the other number is 3. And same thing for when you're dividing. They have to be the same for you to combine them. Now, please keep in mind that the exponents are allowed to be negative, right? If you have 3 to the power negative 13 divided by 3 to the power of positive 7, then still, you just take negative 13 minus 7. You just subtract them, right? It doesn't matter if it's positive or negative. The rules are still the same, okay? And then we have the power rule. So if we have something like 3 to the 5th power, and then all in parentheses to the 6th power, that's when we multiply the exponents, right? So 3 to the 5th power, and then in parentheses raised to the 6th power, that's 3 to the 30th power. So make sure you know that distinction between 3 to the 6th power times 3 to the 5th power, which is 3 to the 11th power, and 3 to the 5th power to the power of 6, which is in parentheses to the 6th power. So make sure you distinguish those two. And then, of course, if you have a fraction and you're going to raise the fraction to a power, you need to raise the numerator to that power and raise the denominator to that power. And the reason for that is because when you multiply fractions together, all the numerators multiply together, but also all the denominators multiply together. So if you have x copies of a over b, then that's going to be multiplying a by itself x times in the top, and multiplying b by itself x times in the bottom. So make sure you know that. In other words, if you take the exponent of a fraction, the exponent distributes to the top and the bottom. Okay, and then of course, if a is not equal to 0, then a to the 0 power is always 1. So 2 to the 0 power is 1. 5 to the 0 power is 1. 1 to the 0 power is 1. It's always 1. Negative 5 to the 0 power is 1. 2/3 to the 0 power is 1. Pi to the 0 power is 1. Square root of 2 to the 0 power is 1. It's always equal to 1, except if a is 0. Now, you'll never have to worry about 0 to the 0 power. It's undefined, so if you ever see it, you just have to remember that it's not equal to anything. However, 0 to any power is 0, unless it's 0 to the 0, of course. That's the only exception. So, yeah, just make sure you remember that. And then negative exponents. You need to remember this. So if you have like 3 to the negative 5th power, that's the same thing as 1 over 3 to the 5th power. Okay? And then also make sure you know that 1 over 3 to the negative fifth power is 3 to the fifth power. And then, yeah, so I heard this thing before where I had a teacher that said that if you have a number raised to a negative exponent and it's in the numerator, then like that negative exponent you can think of as like, oh, like when my kids are bad, I send them down to the basement, right? And they become positive. They become good when they're down there because they become quiet or something. So if you have like 3 to the negative fifth power in the top, you're gonna, since the negative 5, you're gonna send it to the bottom, and then it becomes 3 to the fifth power when it's in the bottom. And then likewise, if you have like 2 to the negative 10th power in the bottom, then that becomes 2 to the 10th power in the top. So if you don't like negative exponents, you can always just send them to the opposite side of the fraction bar, the vinculum, I think it's called. Yeah. And then fractional exponents. So if you have a to the x over y power, fractional exponents, it's the same thing as just, well, if it's x over y power, then the y is like the yth root. Okay? So if you have like the 3/2 power, that means you take the square root and then you cube it. Or you cube it and then take the square root, right? Because if you have a to the x over y power, that's like a to the x times 1 over y power. And of course, multiplication is commutative, so it doesn't matter what order you do the exponents in. So yeah, there is the fractional exponent rule. And of course, we'll do examples because, looking at rules and generalities is kind of hard to figure out. But here, make sure you understand these two problems in particular before moving on. These are good examples of fractional exponents. Now, they're both going to be integers. They're not going to be too crazy. You can read the little note up there about fractional exponents if you're still confused. But I'll give you some time to rewrite each of these expressions. I don't know why it says rewrite in radical form. You can do that if you know what that means, but just simplify as much as possible. They're both going to be integers, so just see if you can do it. And remember, the over 4 means fourth root, and the over 3 over there means cube root. Okay, good luck. Okay, hopefully that was enough time to work on these. Um, so there's two ways to do both of these problems. Um, you can do the fourth root part first, or you can take it to the fifth power first. Now, obviously, for 16 to the 5/4 power, that if you take it to the fifth power, that's a huge number, right? That, and then you have to take the fourth root of that. Like that's how are you gonna do that without a calculator, right? So the first way is obviously better. So 16 to the 1/4 power, and then we'll raise it to the fifth power. Because remember, if we have 16 to the 1/4 power and then take all of that to the fifth power, the exponents multiply. So that's the same thing as 16 to the 5/4 power, right? So 16 to the 1/4 power is just the fourth root. So what number to the fourth power is 16? Well, 2 to the fourth power is 16. So that's 2. And then we take 2 to the fifth power, which is 32. The second problem, we have -8 to the 2/3 power. Yeah, either way is fine for this one. If you want to square -8 first and then take the cube root of that, or if you want to take the cube root of -8 first and then square the result. Either one's right. If you take the cube root of -8, the cube root of -8 is -2, because -2, all of that cubed is -8. And then if we take the square of -2, we get 4. And then if we do it in the other order, if we first square -8, we get 64. And then we have to take it to the 1/3 power, but the 1/3 power is the cube root. So what number to the third power is 64? Well, 4 to the third power is 64. So the answer is 4. And notice our answers match doing either way. So you obviously have a lot of freedom, but there's always probably going to be an easier way. You want to pick the easier way. Yeah. Let's practice a little bit more with a couple more problems, and let's see how you do on those. Oh, and when you see the radical sign and the little number sitting on the left side of the radical sign, that tells you what root that it wants you to take. Okay, so try these problems a little bit. Refer to the list of exponent rules if you're not sure. All of the exponent rules should be enough to figure all these out if you apply them correctly. So good luck, and I'll give you a few minutes to work on this. Alright, hopefully you had a chance to work these out. Okay, so we have 144 times x to the negative 12 raised to the 1/2 power. So there's one of the rules that says that if we have two numbers multiplied and we're taking the product to a power, then we have to distribute the 1/2 to both terms. However, first, the solution here actually, remember when we said that if there's a negative exponent, we can kick it down to the denominator? That's perfectly fine. So we can actually do that instead. But if you want to do it the first way, you just distribute the 1/2 to the 144 and distribute it to the x to the negative 12. So 144 to the 1/2 power, that is 12. And then x to the negative 12 to the 1/2 power, we just multiply negative 12 and 1/2, we get negative 6. So it's 12 times x to the negative 6 power. And then if we do it this way, where we first kick down the x to the negative 12 down to the basement because we prefer it that way, which, I mean, I certainly do. I don't like negative exponents too much. So we have a fraction, and we want to take the fraction to the 1/2 power. So what we're going to do is take 144 to the 1/2 power, which is 12, and we'll and of course the 1/2 power, that's the square root, right? And then x to the 12th to the 1/2 power, we just multiply the exponents. 12 times 1/2 is 6. So we have x to the 6th in the bottom. And also, just so you know, we have problems like this. It's always standard form or standard practice to not have any negative exponents in our answer. So like if we did it the first way and we just distributed the 1/2 right away, we would get 144 to the 1/2, which is 12, and then x to the negative 12 times 1/2, which is x to the negative 6. But we would kick the x to the negative 6 down to the bottom, and we get 12 over x to the 6th, which is what we get when we do it either way. Okay, and then problem B, we have this fraction, and we're going to take the whole fraction to the negative 1/3 power. Now, when we take a number, like say we take 3 to the negative 2nd power, that's like 1 over 3 to the 2nd power. And if we take 1 over a fraction, that's the same as taking the reciprocal of the fraction. And remember, reciprocal just means we flip the numerator and the denominator so that the denominator is now the numerator and the numerator is now the denominator. So if we flip the fraction, we get x over 8, x to the 7th y cubed, and now we're going to take all of that to the 1/3 power, because the negative part of the exponent did the job of flipping it, and now we need to do the 1/3 power. So, however, before we take everything to the 1/3 power, we notice that we can simplify a little bit. Because there's an x in the top and an x in the bottom, we can cancel out an x. So we take out the x in the top, we're left with a 1, also known as the empty product. If we divide out everything from an expression, we're going to be left with 1, and that's often referred to as the empty product. 0 is the empty sum, by the way. So if you have a sum of terms and you subtract them all off, you're going to be left with 0. Okay. So, okay, well, the 1/3, 1 to the 1/3 power is 1, because 1 to any power is 1, including 0. But yeah. Also, 1/3 power is cube root, and the cube root of 1 is 1. So, yep, the top is 1. Now the bottom, the cube root of 8 is 2. And the cube root of x to the 6th is x squared. And the cube root of y cubed is y. So this problem worked out really nice. You could also do x to the 6th and then multiply the 6 by 1/3, which is 6 times 1/3 is 2. So same thing. And y cubed, well, 3 times 1/3 is 1. So we just get y. You could think of it either way. You can think of it as the cube root, if that's easier, or you can think of it as taking it to the 1/3 power. They're both equivalent concepts. Okay. So now, let's take a look at your homework problems for tonight. I'm going to give you some exponent problems and then one more additional problem. So here are the problems that I want you to do by tomorrow. So the first three problems, again, you can ignore the change to radical form. I'm not sure what that means. It probably means like using cube roots and square roots and like writing that and then taking that root to some power. But you don't have to do that. Just simplify however way you know how, or whatever way you think is best. Just get the right answer. So you're going to simplify these problems, and then for 4, 5, and 6, you're going to simplify these as well. So notice the first three problems don't have any variables in them, so they're going to be a number as an answer. And then the second set of three problems, there 4, 5, and 6, they're going to be have variables in them probably, unless they all reduce to a number. And then you have an additional problem. So you have 7 problems for homework today. So this problem I decided to give you today because this is a problem about factoring. Now we did most of our factoring yesterday, and that was what yesterday was mostly about, and then we reviewed a little bit of it today. But this problem, I just kind of felt like there was some exponent stuff in this problem that you needed to be careful about. And instead of showing you the problem, I thought that I could assign it to you instead, just because it's good practice for exponents as well. So yeah, try to factor this into 4 factors. So non-trivial factors are just factors that aren't equal to 1. So like, don't write 1 times 1 times 1 times 8 to the 2x minus 27 to the 2y. Right, so just find 4 factors to multiply to give you that, and that's your job. So factor it in terms of x and y. Obviously, there's gonna be differences of squares or differences of cubes involved. So yeah, so thinking about those notions, try to factor this using what we've learned, and also be careful about exponents. And yeah, I'm excited to see you all tomorrow, Wednesday. We'll meet at from 2:30 to 4:30 at Gear Library. Okay, see you then. Bye-bye.